error in the assignment, right? Everyone saw that. It was, should have been a probably amplitude, and it wasn't a normalized, it was a probability, so it's a good way to.
Made the expectation value nice and clean.
So I apologize. There is another assignment coming. As I mentioned, I'll be on travel Thursday afternoon. And so there won't be a problem session this week. Gopi, are you available that time? Or does
Yeah.
Carl have his, there's no?
No, not this time.
Okay, so maybe during those hours you can hold the office hours. I'll discuss the homework with you. And you can meet with folks in 190 this time,
Okay.
or in your office, or in room 30.
Yeah.
Okay, we'll discuss that. I'll send a message to everyone to let them know what the schedule is. But as we saw, unfortunately, there's a room conflict at 11 o'clock in room 190. So there's just no other room available. So here's what I propose. The chair seminar finishes 10:15-ish. So we'll get started at 10:15 in 190, and I'll go over the problem set with you, make sure everyone understands what's going on, and address any questions, and then we'll get to work on it, and we can continue. Come around. We'll use the front lobby here for continued discussion from 11 to noon. All right.
And that'll start next week.
That'll start a week from Friday. But I'll send the marching orders for this Friday. Okay. And the first exam will be sometime the week of September 29th. We'll have to find the time. I don't want to have it in class, but I'd like to have more time for you to do the exam. I'd like to do it in the evening, but I know that people have other courses, so I'll try to find that time for you. All right? And that will cover material through the next problem set. Okay? And basically through the lectures this week. All right. Very good. So last time, so we were talking about quantum measurement, as we have for a while now. And we introduced this one standard paradigm that helps us to understand a particular example of quantum measurement, the Stern-Gerlach apparatus, which is a way of measuring the projection of angular momentum along a certain axis. Okay? And in particular, if the total angular momentum is spin angular momentum, then it's a measure of the spin projection along some axis. So silver atoms are atoms that in their electronic ground state have only spin angular momentum. Their spin 1/2. It's coming solely from the spin of the valence electron. So when you create a collimated beam and you send it to this device, what you find is that it separates into two beams corresponding to the two possible eigenvalues of the observable SZ. Okay? And so if you, say, block one of these beams, then you've done a projective measurement, and with probability 1/2 coming out of 7, the atoms in this beam are projected into the state spin up along the z-axis. Okay? So this is an example, sort of a projective measurement. It's not quite the paradigm of projective measurement in the sense that in a standard paradigm, it's projected into one of the eigenvectors corresponding to the eigenvectors of the observable being measured with a certain probability. Here, well, we block this beam. And if we didn't block that beam, Did we really do a measurement of spin up and spin down if we didn't look at it? Well, the answer is no, not really. It kind of depends. I mean, if this were in the vacuum and there was no other perturbing noise, then in some sense the atom is in a superposition of this beam and that beam. It's like sending it through a beam splitter. And as we said, an atom could be here or here, but we really shouldn't say that it's one or the other. It's in a coherent superposition of the two. And if we recombine those two paths, we would get interference. Okay, and the other thing we talked about briefly, and I just wanted to mention again, that it's a concept that is perhaps less familiar, but nonetheless important, and that's the notion of a weak measurement, a measurement that doesn't distinguish necessarily between the eigenvectors of the observables completely, maybe partially distinguishes between those alternatives. So, for example, if we have the same device, but we put a screen too close in to the point that the beams haven't really separated well enough, and we said collected a histogram of the counts, we would see this kind of double hump structure, but the tails overlap. So there's no way to completely distinguish whether the atom is in this hump or that. If it lands here, well, I can't really say what its state was, right? Whereas if I had these two things and I put the screen over here, then these two alternatives, if I can give them color if I like, because it's kind of nice once in a while. These two alternatives are, for all intents and purposes, other than a tiny, tiny, tiny bit in the tail that you can neglect, completely distinguishable. So if it lands here, we would say, yeah, the atom was spin up along Z. If it lands here, we would say it's spin down along Z. But we can't perfectly correlate where it lands on the screen here with what spin state it was, right? We can kind of do it, but only with some confidence. So the measurement outcomes here correspond to, say, taking this data and fitting it with these two curves and saying if it lands in this thing, I'll call it the plus alternative. And if it lands in this guy, I'll call it the minus alternative. So they're two alternatives, but they're not orthogonal. They're not completely distinguishable. And so each one of those outcomes is associated with a POVN element where, say, for example, this guy is, with 95% confidence, I would say it was spin up, but maybe 5% I would say we're spin down. And if it lands in this guy, I'd say with 95% confidence it was spin down, but 5% confidence it's spin up. So it's a measurement that says maybe. Maybe it's spin up or maybe it's spin down. I can't tell you for sure because my measurement can't tell the difference. If it lands here, what do you say? Okay. So in this case, this is a resolution of the identity. That's to say, if you look at this, the sum of this plus this is the identity, right? And we would say, we can predict the probability the spin is going to land in this yellow hump is equal to this. And the probability it lands in the minus hump is that. And that's a generalization of the Born rule. Right? Okay. So, last time we were discussing a little bit at the end of the lecture, how do we think about the state that comes out of this oven? Not the oven, the oven. And before I get to that, let me raise the following question. We loosely defined a pure state. We said a pure state was a state of the quantum system where we have maximum possible information consistent with quantum mechanics. There's no information missing. We have all we could possibly have. That's when we have that, then we assign to the system a pure state, and we said such states could be mathematically represented as kets or vectors in Hilbert space, and those vectors we generally think are normalized, and the overall phase is irrelevant, right? So, question, how do I prepare the system in a pure state? Any ideas?
The Stern Gerlach.
Sure.
When you block the lower part and you only have the plus Z, that's, you're certain about that.
Exactly.
But
So that's it. So that's how you make a pure state. If you, so a preparation procedure do a projected measurement of a permission observable and keep the state corresponding to some non-degenerate eigenvalue. Then we are guaranteed, if we've done that, if we could do such a measurement, then we have totally prepared the system with as much information as we can. This is as fine-grained a measurement as we could possibly do. We can't get any more. This is, of course, not such a measurement. If we did that and it landed somewhere, we blocked, say we blocked, you know, this guy over here, we wouldn't know for sure. So we wouldn't have prepared. There's missing information still. But if we did this, we prepared the system in a pure state. Okay? So, as I said last time, we're just to simplify the notation, instead of drawing, you know, gradient magnetic fields and pointed north and south poles, I'm just going to say there's some Stern Gerlach device that's a box. It's a black box, and it measures, for example, SD. Okay? And so, whatever comes into there, if we have these two, it has these two output ports, we're going to block this guy, then we have prepared the system in that pure state. Okay? Now, the fact that we have prepared the system in that pure state doesn't mean that every measurement we do, we're going to be able to predict its outcome with perfect certainty. Not every measurement we do on a pure state has an outcome that is deterministic with probability 1 or 0. I mean, some are and some aren't. So, for example, if I
measured this again as z, then this with unit, I know with unit probability that it's going to come out absolutely here and nothing's going to come out here. So that's with unit probability. So with probability 1, that happens. If I prepared it in a pure state, and I can know the probability of this happening again is 1. In contrast, of course, if I measure in some non-commuting observable, so I prepared the pure state up along z, but then I measure along the x-axis, then the measurement outcome is random, even though it's a pure state. And that is the bizarreness of quantum mechanics, that randomness, even though I have as much information as I can, still I can't predict the outcome of every measurement I do. And so I'll get spin up along x or spin down along x, each with probability 1/2. Random. Okay? So, what about the state of the system coming out of the oven? Well, let's say we did a series of measurements. So here I have my oven. Atoms are coming out of it. And I put it through an SZ, Stern-Gallic analyzer. And we said that we get right? Suppose that I took this oven and I took the atoms and I put them through a Stern-Gallic analyzer along the x-axis. What would I expect? Same thing, right? With 50% probability it'll go in the x up and 50% will go in the down b. In fact, of course, there's nothing special about x, y, or z, or any direction in space. We expect, just intuitively, and we can then think about how we get this more formally, that if I analyze this with a spin analyzer along any direction in space, it doesn't matter x, y, z, or along this. There's nothing assumed in the oven. The oven is isotropic. It doesn't know what this is versus that. There's nothing to tell it, assuming that that symmetry is not broken. And so no matter what I did, no matter what I would find for this state, spin up along that axis with 50% probability, and spin down along that axis, for no matter what that axis was. Now, what is the quantum state that we would assign to the silver atoms coming out of this oven, which would have this kind of probabilities? If it was spin up along z, that would agree with that, but it wouldn't agree with that. If it was spin up along x, it would agree with that, but it wouldn't agree with that. If it was spin up along some other direction, well, it wouldn't agree with that. So it's spin up along no direction. It's spin down along no direction. So what the heck is it? Well, the answer is, it's not a pure state. It's not a state. These measurement results are not consistent with any pure state. For any pure state of a spin when that particle is spin up along some axis. So there's got to be something more than pure states in physics. And the answer is yes. So here's the one I'm going to fine, it's a somewhat contrived example, but not completely nuts. Suppose that I have a preparer, and the preparer has access to both quantum randomness and classical randomness. What do I mean by that? Suppose that, so inside, now I'm going to draw my little Stern-Gellner device just to emphasize this thing. And you know, I'll just forget about the width of the beam and say that. So each atom either goes up or down depending on if they were to measure them, sometimes they come out here, sometimes they come out here, sometimes they go. Let me just instead of drawing it that way. I don't know which one we're in. Okay? So this is my Stern-Gellner apparatus, and it's, say, oriented along the z-axis, for example. Okay? Now, suppose the preparer, this is such a deadly beam that's coming through that the preparer can measure this one atom at a time. Okay? And the preparer then can determine whether the atom is spin up or spin down. She collects all her spin-up atoms in some magnetic bottle, and she collects all her spin-down atoms in another bottle. She has prepared two collections of pure states. She has a bunch of spin-up atoms, and she has a bunch of spin-down atoms in her possession, in her bottles. Okay? And now what she does is she flips a coin. Okay? So, she flips a coin. It's a quarter. And we're heads and tails. Okay? So she flips a coin. And it could be either heads or tails. And if she gets heads, she spits out of this device, which is now inside a big black box that we can't see inside. She spits out an atom. And she chooses whether to send me one of these or to send me one of these, depending upon whether she gets heads or tails. Okay? Does everyone understand the idea? So she can send me one atom at a time, either a spin up along Z or a spin down along Z. Okay? So she decides with probability, so she has a probability for sending me spin up if heads. And she sends, with some probability, she'll send me spin down if tails. Okay. So these atoms are coming at me. And now I can analyze them. Suppose, for example, I do a Stern-Gellner analysis along the z-axis. I'll get one of two possible outcomes, assuming I separate my beams sufficiently to resolve them. What probability will I see spin up along Z? Depends if it's a fair coin or not. Suppose that that coin has this probability to show heads and this probability to show tails. So with what probability will I see spin up? This probability. Because if she sent me spin up, I'm going to get spin up. If she sends me spin down, I'm going to find spin down. I don't know which one she sent me. So with probability, this is the probability of heads, I'll see this. And with the probability of tails, I'll say this. Is that clear? It's nothing to do with the Born rule. It's just that there were these two alternatives. She might have sent me a spin-off atom. Now, of course, this is subjective. I don't know what she sent me, but she knows. So she, with probability 1, can predict which way it's going to go. But I don't know. So from my point of view, I see a bunch of random up and downs. From her point of view, she goes, that one's going to go up, that one's going to go up, oh no, that one's going to go down. Because she knows whether she got heads or tails. She doesn't talk about that. All right. But suppose now, instead of analyzing, analyzing the state of the spins that come out of this contraption with a Stern-Gerlach apparatus along X. Thank you. And along Z, suppose I do it along X. So there's these two possibilities. What is the probability that I'm going to see X, and what is the probability I'm going to see spin up along X, and what is the probability I'm going to see it spin down along X? Let me say this slightly differently, just so I don't confuse notation. Let me call this the probability of heads and the probability of tails. Okay? So what is the probability in this kind of analyzer? I will find, say, spin up along X, given that the preparer is sending this. Well, here's how I would calculate it. There is the probability to find up along X, given she, the preparer, sent spin up along Z times the probability she sent me that. Or she might have sent me spin down, right? And if she sends me spin down, then I have to say, well, there's a probability of finding spin up along X, given that she actually prepared spin down along Z. And I have to weight that by the probability she actually sent me. Is that clear? This is logic, right? This is just classical conditional logic. She might send me this. She might send me that. I don't know. But she's going to send me one of those. That's the promise. And I would say, well, I know she also, showed me her coin and whether it was a fair coin or how many times it's more likely to come up heads versus tails, right? So what is this? The probability to find this, given that she said that, what is that? How do you calculate that?
Yeah, it's a half.
It's a half, and how do you get that?
The absolute square root.
Right, you have the square of the, use the Born rule, times the probability she actually sent me that. That was probability of heads, right? Plus, if she sent me down along Z, and that happens with the probability she got tails. Okay? Or, if I wanted to say the probability she sent me this. Either way. So this is the probability to get plus x given that she sent this times the probability she sent this times the probability to get up x given that she sent down along z times the probability she actually sent down along z. That's logic. And in this particular case, what is the answer? As was said, this is a half, and this is a half. In this particular instance. And this thing is equal to a half then times the sum of the probabilities of heads or tails together is 1, is a half. So in this case, I'll see random 50-50 chance. Okay? So, this state, the state of the that I assign to the spin of the atom here, is not a pure state. It's not a pure state because I'm missing information. That missing information is whether she got heads or tails. The information's there, I just don't know it. If I knew it, then I would say this guy's up along Z, this guy's down along Z, this guy's down along Z, this guy's down along Z, depending on the sequence of heads and tails. But she knows it, but she's keeping that information from me. And I'm missing that information. Okay? So this kind of state, the state of this spin, is what we would call a statistical mixture. She has these bottles of spins, and she can mix them together any way she likes. She can mix them. This is what we would call, this is an example of what we call a mixed state. Okay? So this state is a statistical mixture weighted by different probabilities. So I have some probability of this guy in the mixture and some probability of this guy in the mixture. Okay? This should be contrasted with what we would call coherent superposition. What is a coherent superposition? A coherent superposition, for example, is this. This state is not a mixed state. It is a pure state. Doesn't mean that every measurement I do will have a definite outcome, but it's a pure state. And that state can have the same probabilities for measurement outcomes along, say, the z-axis. The probability of seeing spin up along z could be this, and the probability of seeing spin down along z is this. And that could be the same as the statistical mixture I have of these guys. So if I measured this guy just along the z-axis, I couldn't tell the difference from this, right? It could have been there were coin flips. So what's different? The difference is interference. Because in the statistical mixture case here, we saw in this case the outcome of seeing up and down along x is a half, right? Suppose the probability that heads equals the probability that tails is a half. Okay, fair. You have an equal statistical mixture of spin up and spin down along the z-axis. Okay? So the probability to find up along x or up along z and down along z equals a half. And the probability to find up along x and down along x is also a half for this statistical mixture. But, right, that's what we just saw. But, if I have a pure state, let's suppose I choose this guy. This state, the probability to find up along z and the probability of finding down along z is a half, just like this. But the probability to find up along x is what?
1 or 0?
1. It's this guy is 1. This guy is up along x. And the probability to find down along x is 0. Now how the heck does that happen? It happens because of interference. Even though this is a 50-50 chance of up along x, it's not a statistical mixture of these two.
So the pure state would be the person sending the particles out.
So this is an important point. States are subjective. From the point of view of a preparer, the state is pure because she has complete information. From the point of view of the observer, the state is mixed because he's missing the information. Right? It's like the chalk in my hand. I know where it's going to be, so it's a deterministic outcome. But for you, it's a random outcome. Okay, but that's about what's weird in quantum mechanics is even when you have complete information, you still can have randomness. Okay, so let's talk about this interference stuff once again. So, let's say we have the pure state side, which we said is a coherent superposition of spin up along z and spin down along z with that particular set of probability amplitudes which we know is the state spin up along X. Okay? The probability to see down along X is, according to the Born rule, that. Okay? And that is equal to, just writing it out in this superposition, just to emphasize a point. I will not trip, I will not trip, I will not trip. Right? Which is equal to okay? Being very pedantic and slow here. And now let's square out the term. I have the square of this term plus the square of that term plus the cross terms. So that's equal to the square of the first term okay? Those are the squares of those terms. And then the cross terms. So the cross term, I have this times the conjugate of that, right? Because you have to multiply it by its complex conjugate. Okay? Now let's take a close look at this expression. These first two terms are exactly what we had for the statistical mixture. This is the probability of seeing spin down along X, given that the state was actually spin up along Z, times the probability that it was spin down along Z. And this is the probability of finding spin down along X, given that the state was actually spin up along Z, times the probability that the state really was spin down along Z. And that's what we would have if we had a 50-50 statistical mixture of up and down. But that's not the whole story. I have these terms, which are the cross terms, which are the interference between these two alternatives. So we don't know. It's in a coherent superposition, and those two terms interfere. Okay? So these are the classical alternatives. So this is classical statistical reasoning, logic, and this is quantum interference, illogic. And what is it in this case? Well, here we have to go through and do all that. This guy is equal to 1 over root 2. This guy is actually minus 1 over root 2. And so this is the conjugate, minus 1 over root 2, and plus 1 over root 2, if you do it out. And so this is equal to a half. This is a half. So I have a quarter plus a quarter is a half. And minus a quarter, which is minus a half, which is 0. Complete destructive interference. And that's what we expect. If the state would spin up along X, the probability of being spin down along X is 0. And the reason is there's destructive interference. That's one way of interpreting it. I don't know if I think the reason is, but a way of thinking about it is that whereas classically you would have these two alternatives, quantum mechanically, those two alternatives destructively interfere. So the distinguishing feature of the pure state from the mixed state is the ability to see interference between those alternatives. All right. Questions so far? All right, so now, if we want to count, remember what we said was the job of our quantum mechanical formalism is to allow us to calculate the probabilities of outcomes of measurements, to predict the outcomes of measurements to the best of our ability. And we developed this formalism so far to do that. We had the state vector, we have Born's rule. When we have statistical mixtures, life has become more complicated. I have to say, well, if she got heads, then she sent me this, and if she sent me this, then this is the probability, and I have to go through all these extra steps. And it seems like I should be able to encapsulate this all. There should be one thing I call the state of the system that allows me to calculate the probability of outcomes, whether or not the state is pure or mixed. Okay? So there should be some generalization of the state from this, the ket. There should be some more general state of the system. And that more general state of the system is what we call the density operator. So let me tell you about the density operator. How many people have seen the density operator before in their previous studies of quantum mechanics? A couple of people. Not a common deal. But, you know, the state that comes out of the oven is a density operator. That's to say, that's our state assignment. We can't assign a pure state because we're missing information. Information's there, we just don't have it. It's like the coin flip. All right? So what do I mean by that? Well, so let's look at what we did in this case with the heads and tails. So what we said was, so suppose we have a statistical mixture of spin up along X or Z, doesn't really matter, and spin down along Z. Prepared with relative probabilities P plus and minus. Okay? Within those coins. That's the coin has that. Okay? And I want to find what is the probability to find, say, spin up along an arbitrary direction. I'm going to have a Stern-Gerlach analyzer. It's going to analyze it along some direction. I don't care, X, Y, Z, 45 degrees between the X and Y axis. Who cares? Some axis in space. How do I calculate? Well, we just said, have to argue logically. There's the probability I'll see spin up along Z, given that the preparer sent me spin up along Z. There's some probability that she did it. And if she sent me spin down along Z, then this is the probability of finding spin up along that direction, and I have to weight that by the probability she actually sent that to me. Okay? This is a statistical mixture. There's no interference between these two alternatives. Okay? So let me rewrite this this is equal to this times its complex conjugate. And the complex conjugate is reversing the bras and the kets. Okay? And so I'll write this like that. All right? And because the inner product is linear, I can rewrite that probability in the following way. This is equal to, this probability is equal to that rod, and then I'm going to write this as the probability she sent me up times that projector plus the probability she sent me down times that projector. You agree that those two things are equal? Right? So look what I've done. Everything about the preparation procedure is in the brackets, is in this thing. And everything about how I'm analyzing the system is outside. So this is about the preparation procedure. This is about the state of the system that I know. So this operator is an operator we call rho. And this operator is the density operator. The term density is such an arcane and it's a stupid name at this stage. We really should call it the state operator. Because this is the state of the system. Now, let me emphasize a fact. This is an operator, but it's the state, okay? You have learned in the past that states are vectors and observables are operators, but that's just the way you've learned it. We can define the state as an operator. And we do, and we should. And it's, what do we want from the state? What do you want from these? What you want is, you want to be able to calculate the probability of outcomes of measurements given the state. And you can do it. If I want to find the probability of an outcome, I just take the expectation value with respect to that outcome. And that is the probability of seeing that. Because this, we just calculated. It's just a new piece of mathematical tools and formalism you need to learn. All right? So the density operator is the most general state of the system that you could possibly have in quantum mechanics. It includes pure states and general mixed states. If it's a pure state, it would be if one of these probabilities were 1 and the other was 0, then it would be a definite state, we know. But if these probabilities are not, then it's a... So, let me look at my cheat sheet here and remind myself of the order I might have thought about doing these things. Right. Okay, cool. So, this is my, I'll continue here. This is my state. Let's say we have the following things. Say things a little bit more generally now than just spin 1/2 or even a two-sided coin. I could say a general statistical mixture can be thought of as the following. The preparer has or sends one of an ensemble of pure states, and she does so with probability pi. So now she doesn't have just two bottles, she has a bottle of as many different states as she likes. They don't even have to be orthogonal states. She has a bottle of spin up along x, a bottle of spin down along y, a bottle of spin up along this direction, a bottle of whatever she likes. And she sprinkles them in. She rolls the dice. She has a 12-sided dice. She has 12 different pure states she can send. And she sends them off. Okay? She mixes with that probability. What is the state of the system then? Any guesses? Any thoughts? So here she had two choices. She had just a coin with two, and she had a bottle of spin up along Z and a bottle of spin down along Z. But now she has all kinds of bottles of all kinds of spins along all kinds of axes.
Would be a 12 by 12 matrix for your,
Is it two levels?
We'll get to the matrix business in a bit, because that's a
or
little...
sum of 12.
Yeah, the sum on
Sum
five.
of- Exactly.
Yeah,
Because it's a little subtlety there. I'll come to the question of the matrices in a moment. It's the sum over all the members of the ensemble weighted by the probability times these projectors. Okay. That is what we would call a statistical mixture of these size. If this is a spin 1/2 particle, even if I have 12 different members of the ensemble, this is still a 2 by 2 matrix, because it's still a two-dimensional Hilbert space. Okay. There's a subtlety there. Okay, so what is a pure state? A pure state, what is the density matrix for a pure state?
Just, there's no sum, there's just a one. And
It's just one, it's just this. There's some side, and it looks like that. That's a pure state. A pure state is a projector along that side. Okay. So if it's a pure state, there exists a side for which this is true. Notice one of the nice things about the density operator formalism is that it gets rid of the phase ambiguity. Because the overall phase of psi cancels out here. All right. What about a thermal state at temperature T? Well, you've learned in your statistical physics course that if you're at thermal equilibrium at temperature T, we don't know for sure what the state of the system is. We can only say with a certain probability. We have a Boltzmann distribution of possible energies the system can be in. We know that probability distribution, the probability of having a certain energy, is the Boltzmann distribution over the partition function for the, right? So what is the quantum state of the system associated with this? Well, a statistical mixture of different energies. It's not a coherent superposition of these different energies. It's a statistical mixture. And so what we would say is a sum over all energies, let's say there's the nth energy, E times the energy, nth energy level. And that's what's coming out of the oven. Okay. All right. Very good. So, now what we want to do is delve into this a little bit more deeply to understand the nature of the density operator, try to develop a little bit more intuition about it, how we use it to do calculations. Well, before I do that, let me say, maybe I should say the following things. Let's just say, let's understanding the density. Okay. Suppose, let's just talk about things a little bit more general, a little bit. So what we just said is that given the state rho, say for spin 1/2, the probability to find, say, spin up along some arbitrary direction was equal to this. That's what we just showed. Okay. We can think about this as a diagonal matrix element. What about the off-diagonal matrix elements of rho? What do they tell us? Well, let's take a look at a pure state. Consider the state which, let's say we have a state which I'll write as a ket, which is some superposition of up and down. An arbitrary pure state is of that sort, right? And let's write it as a density operator. So now we just got to plug it in. Okay, so let's multiply that. What do you notice about this? Well, these first two terms look like the statistical mixture of up and down. But these terms, the off-diagonal terms of the matrix elements, don't look anything like statistical mixtures. Because these are the terms that are related to what we call the coherence. Okay? So, written as in a matrix representation, in the basis of, say, spin up and spin down along C. Let's look at two different cases. Suppose I have, in one case, a statistical mixture of these two guys with mixing probabilities. Rho is equal to this and this. What is the matrix? As a 2 by 2 matrix where this in this order.
P plus Z, P minus Z on the diagonals?
P plus and P minus on the diagonals, and what about the off diagonals?
0.
0. This guy has off diagonal matrix elements that are 0. Okay, contrast. Pure state. The one we wrote down over here, which is some arbitrary superposition of these guys. What is the matrix representation of this density operator?
Same thing on the C plus squared and C minus on the diagonal.
C plus on the diagonals, C minus.
C plus the C star minus on the top right, and then on the bottom left.
Exactly. Okay. So, we could have two states which have the same diagonal matrix elements, but very different diagonal matrix elements, off-diagonal matrix elements, where they would have look the same as if you measured them X, but if you, and Z, but if you measured them in X, they would show very different. And these off-diagonal matrix elements are what we call the coherences, as opposed to the populations. So we could say, are you up or are you down? And then you can ask, can up and down interfere with one another? The off-diagonal elements of the density matrix are the things that are telling me whether or not those two alternatives can interfere. Of course, that's a basis-dependent question. It's interfere in that respect to that. So that's an important point. So let me conclude this part of the discussion, which is something a little bit more general.
I have a question.
Yes, please.
It's probably maybe a dumb question, but can we diagonalize the matrix?
Yes,
And then-
it's not a dumb question.
And then like perform, I guess, the classical probability?
Absolutely. So yes, it's a very good piece of intuition, something we'll talk about probably on Thursday. Of course, this is a Hermitian matrix, and so we can diagonalize it, and its eigenvalues and eigenvectors are important ways of characterizing the state of the system. You can always think about the density matrix as a statistical mixture of its eigenvectors, weighted by its eigenvalues. If it's a pure state, it has one eigenvalue, 1, and the rest are 0. If it's a mixed state, then it has more than one non-zero eigenvalue, which represents statistical mixtures of more than one pure state. Cool. All right, but before we get there, I just want to say one last thing, just to emphasize this idea of the coherences versus the populations. So let's talk about things just a little bit more generally, not just about spin 1/2 at the moment. Let's just say, let's consider a general state in a d-dimensional Hilbert space. So I don't know, it's some thing, it's got d dimensions. It could be a spin j with 2j plus 1 is equal to d. All right? So, let's say if I have a pure state. I could write it as a cat. I don't have to write it as a density matrix, but you can write it as a cat. And that is a sum over all the elements of some basis. Okay, so this is the basis. Okay, written as a density operator, this pure state is sum over these two indices okay. So the elements of the density matrix, which are called the density operator, which is called the density matrix. People use that term interchangeably. People talk about the density matrix, even when they're talking about the operator. This is the top. So the matrix elements here right? It's bilinear like that. So again, the diagonal elements of this is equal to this, which is equal to the probability to find the off-diagonal elements which, let me write this in terms of a magnitude of each complex number and a phase. Okay, so I bring each complex number C in polar form. It has a magnitude and a phase. Is that clear? So notice that these off-diagonal matrix elements have something to do with the phase relationship between the amplitudes. The off-diagonal elements capture the interference because they have something to do with the relative phases. Okay? So they are the coherences. That's what we call them. These are sometimes called the populations. Kind of stupid name. So, what about when I have a mixed state? Well, when I have a mixed state, then I have a statistical mixture of different pure states. Okay? So, if I have a statistical mixture, of different psi i's, each of which has some potentially different superposition. Okay? So I'll say psi I is some superposition for the ith member of the basis state. Okay? Then my state here is a sum over I, pi, mixing together these pure states. And that is equal to sum over alpha and beta, sum over I, C, I, alpha, C, beta, E, alpha, E, beta. Okay. Weighted by the probability part of it. Okay. So in this case, what we have is the elements of the density matrix have to be averaged. They have to be averaged over the mixing probability. This is confusing. We have two different kinds of probabilities in the world here. We have the mixing probabilities, and then we have the probability amplitudes. They're not actually as separable from one another as I've made them appear. Nonetheless, we can go forward this way. And what we see here is that, in general, this matrix element I can think about as an average over the ensemble of all the different elements. This bar is this average. Okay? So what you can see here is that if I have a mixing of different states, all of which that have random phases, relative to one another, that when I mix it, this is going to generally average out to 0. Which is why statistical mixtures wash out the phase differences and wash out interference. The loss of coherence is called decoherence. And that's the subject we'll talk about next lecture.